Scattering at an interface, normal incidence. We are finally going to move away from waves being inside of a homogeneous medium, and we're going to look at the case where there's two media butted against each other at an infinitely flat interface. And we're going to ask ourselves what happens when a wave hits that interface going from one material to another. First, we need to review the electromagnetic boundary conditions. Then we'll get into the physics of what's happening at that interface. Based on that, we can go on and actually derive equations to calculate reflection and transmission. Electromagnetic boundary conditions. We covered the electromagnetic boundary conditions in prior lectures. We covered the boundary conditions for the electric fields near the end of electrostatics and the boundary conditions for the magnetic fields near the end of magnetostatics. And here were our main conclusions. The tangential components of E and H were continuous across the interface. We also found that the normal components of D and B were continuous across the interface. The normal components of E and H were a little bit different. The normal components of E and H were not continuous across the interface, but we found that the product of the permittivity and the normal component of E is. And the product of the permeability and the normal component of H was continuous across the interface. At this point, we're going to add one more boundary condition. Now that we have a wave and we have a wave vector, we'll see that the tangential component of the wave vector also has to be continuous across the interface because that ensures that the field itself is continuous across the interface. Now let's discuss what's actually happening at that interface. So first, we set up an interface. So we'll have a wave traveling in the positive z direction. And it's traveling in air, and it hits some dielectric medium. And we see that the impedance is different on either side of the interface. And we place the interface in the xy plane at exactly z equals 0. And so medium 1 extends off to negative infinity, and medium 2 extends off to positive infinity. And while it's hard to show, both of these media are of infinite extent in the x and y directions. And I'm not really sure how to convey that on the slide, so we'll just have to remember that. So in fact, these are called semi-infinite media. They're semi-infinite because each of them end at the xy plane, but otherwise they extend off to infinity. Now let's apply a wave to this interface. And so while we're not really showing the wave, we're just showing the information about the wave. So we have its wave vector, that's k, and the subscript I means incident. So that's the incident wave vector heading straight at the interface. So the wave has an electric field component and a magnetic field component. The impedance in this medium is 1, meaning the electric and magnetic fields are the same magnitude. It's maybe a little bit unrealistic to set the impedance to 1 because a more realistic impedance is something like 300 ohms. But just to keep E and H the same order of magnitude, I let the impedance be 1. So E and H are the same order of magnitude now. Okay, so we have this wave and it hits the interface. What happens? Well, perhaps there's a wave on the other side. But how do we know the field quantities on the other side? Well, we know that that wave has to satisfy the electromagnetic boundary conditions. Now, since this wave is at normal incidence, the electric and magnetic fields are both completely tangential to the interface. They have no components that are normal to the interface. So in order to satisfy the boundary conditions, the transmitted wave has to have the same electric field and the same magnetic field. Now we're using the subscript t to indicate that that is our transmitted wave. So our transmitted wave has a wave vector, an electric field, and a magnetic field. And so to satisfy the boundary conditions, the E's on both sides of the interface have to be the same, and the H's have to be the same. However, there's something else that this wave has to satisfy on the transmitted side, and that is the impedance. In the second medium, the impedance is 2. This means the magnetic field amplitude has to be half of the electric field. So if we let the electric field component be 1, that means the magnetic field has to have an amplitude of 0.5. It has to be this to satisfy the impedance condition. However, in order to satisfy boundary conditions, E and H have to be equal to 1. So suddenly we have competing physics. Boundary condition says one thing, the impedance of the medium says the other, and both have to be satisfied. How on earth do we reconcile this? Well, it turns out there has to be a reflected wave. That reflected wave adds to the incident wave so that the total field in medium 1 matches to the transmitted wave in medium 2. So it turns out this is what would happen at the interface. So we have our incident wave. On the other side, notice the electric field has changed its magnitude and the H field. If we look at the magnitude of both of these, we see that the H is half of E, so it's satisfying the impedance. However, at first glance, it does not appear as if the boundary conditions are satisfied because these two electric fields are equal. Well, remember, the reflected wave is adding in here, which if it has an amplitude of 1/3, adds to this electric field of 1 and gives 1 1/3 or 4/3, and that's exactly what it is on the other side. Magnetic field has a magnitude of 1. The reflected magnetic field is actually pointed in the other direction. That is a handedness thing because we're talking about a backward wave. And so the impedance in this medium is 1, so the electric and magnetic field have to be equal, so they're both 1/3. However, since the magnetic field of the reflected wave is in the opposite direction of the transmitted wave, we subtract the 1/3 from this. So the total magnetic field on the reflected side is 2/3. And then on the transmitted side, we see again that it is 2/3. So now we're satisfying everything, the boundary conditions and the impedance of each medium. So the trick here is to remember that it's a wave-by-wave basis to satisfy the impedance. So if we have 100 different waves, each one individually has to satisfy the impedance. When it comes to the boundary conditions, it's a total thing. And so what we're showing down here are the total fields on both sides of the interface. So the total electric field is the sum of the electric fields of incident and reflected, and we get 4/3, which of course matches to the transmitted side. And the total magnetic field is 2/3, which of course matches also to the transmitted side. So it's the total field that has to satisfy boundary conditions. It's the individual waves that have to satisfy the impedance. So the reflected wave is needed to make all of the physics work out at this interface. And maybe that's not as straightforward as we were expecting. The fact that a wave reflects off of something is a little bit more involved than we might have thought. So let's finish with some notes about what happens at an interface. We know that when a wave hits an interface, some could reflect, some could transmit. There's also a third thing that we didn't talk about much. It's a little bit beyond the scope of this class, but if there's loss in either of the materials, we can also have some absorption at the interface. We'll talk about this later, and this is called refraction, but if that wave is incident at an angle, the transmitted wave can be at a different angle than the incident wave. For the normal incidence case that we're talking about here, the wave comes in at 0 degrees angle of incidence and it transmits away at a 0 degree angle. So no angle change here for normal incidence. That only happens when the wave comes in at an angle. Okay, now let's talk about the math. So we have a plane wave at normal incidence. So here's the problem set up, just what we've been talking about, but we need this for when we're writing our equations. So keep this in mind. This is the process we'll go to derive expressions for reflection and transmission. The first thing we need to do is write equations for our applied wave, or the incident wave, our reflected wave, and our transmitted wave. Once we have those general expressions, we will then enforce the boundary conditions. We will set the tangential components of both E and H equal across that interface. We'll end up with new equations that we can then solve for reflection and transmission that we're just calling little r and little t. We'll do one more thing. Given those equations for r and t, we'll do some algebra and actually derive a relationship from r and t. So if you calculate one of them, you can immediately calculate the other. And we'll look at those equations and make some conclusions. So that's the process that we're going to step through. So the first thing is writing expressions for our applied wave, reflected wave, and transmitted wave. So our reflected wave, we'll first just write the electric field. And so it has some amplitude. It's propagating e to the minus gamma 1z. We're giving it a complex propagation constant simply because it leads to a more compact form here. And we'll let the electric field be polarized in the x direction. It turns out it doesn't matter which direction it is polarized. We'll get the same answer. So just for convenience, we'll let it be polarized in the x direction. We will write the magnetic field relative to the electric field using our concept of impedance. So the magnitude of the magnetic field is the magnitude of the electric field divided by impedance. But it has the same complex exponential, and it's polarized in the y direction now. So x cross y will be pointing in the z direction. That's how we sort out our handedness. So we have expressions for the incident wave. We're going to do a very similar thing for the reflected wave. First, we'll write the electric field. So the reflected wave has an amplitude. It has some exponential describing its propagation. Notice there's no negative sign here. That's because the reflected wave is traveling in the negative z direction. The reflected wave, the electric field, is still polarized in the x direction. Now we look at the magnetic field. The magnetic field is the magnitude of the electric field divided by impedance. However, we're also including a negative sign here, and that's to keep the handedness so that AX cross negative AY points in the negative AZ direction. So we have to keep the handedness for our reflected wave. And we have the same exponential describing the phase and possibly attenuation because that's the complex propagation constant. A positive sign here for a wave traveling in the negative z direction. And last, we write expressions for the transmitted wave. Now these resemble very much the applied wave in that we have an amplitude, we have an e to the minus gamma 2z again. The minus is back because we're talking about a wave traveling in the positive z direction. It is still polarized in the x direction. There's nothing to change that. Then the magnetic field is written relative to the electric field. So we have the magnitude of the electric field divided by impedance, the same propagation exponential, and it is still polarized in the y direction. So we just wrote general equations for all of these things. Now we have to start enforcing our boundary conditions and derive meaningful equations from this. We don't know what those amplitudes are. Before we can derive expressions for reflection and transmission from an interface, we're going to have to define what the reflection and transmission coefficients are. So we start with our basic geometry, and we've written here our expressions for the electric field, for the incident wave, the transmitted wave, and the reflected wave. Now let's define what we mean, or let's define our reflection and transmission coefficients. So we will define our reflection coefficient as the amplitude of the reflected wave divided by the amplitude of the incident wave. Our transmission coefficient will be the amplitude of the transmitted wave relative to the amplitude of the incident wave. So to derive expressions for these, the first thing we need to do is write our boundary conditions. We'll get two equations, one boundary condition for E, one boundary condition for H, and then we'll manipulate them and get the expressions for R and T. So our boundary conditions require the electric field on both sides of the interface to equal. So on the first side of the interface, E, and the 0 here means right at the interface, at Z equals 0. So the total electric field on the left has to equal the total electric field on the right. Well, we know that the field on the left is the incident wave plus the reflected wave. And on the right, we only have a transmitted wave. So we plug in our expressions, our wave expressions, and since z equals 0, we have e to the 0 for our exponential since z equals 0. So e to the 0 ends up being 1. Everything is in the x direction, so we can just cancel that. And we have one equation that says the amplitude of the incident wave plus the amplitude of the reflected wave equals the amplitude of the transmitted wave. That's one equation. Now we'll look at the boundary conditions for the magnetic fields, but we start off with the same equation saying that the total magnetic field in medium 1 has to equal the total magnetic field in medium 2 right at the interface. On the left, we have the magnetic field of the incident wave, we have the magnetic field of the reflected wave added together, and on the right we only have the magnetic field of the transmitted wave. Then we replace these H fields with our expressions for the waves. We have these e to the zeros again because z equals 0, so they'll cancel out. Everything's in the y direction, so that will cancel out. And we're just left with a second equation. A couple differences between this equation and the one on the previous slide. Notice we're dividing by impedances here. We've replaced our magnetic field terms with electric field terms divided by impedance terms. So in this equation we have impedance terms. We also have a negative sign here. Remember, that's because the reflected wave we had this handedness thing. The magnetic field's pointing in the other direction because we have a wave traveling in the negative z direction. So this is our second equation, and it's from these two equations that we'll derive expressions for r and t. So here's our two equations that we're starting with. This equation on the left is what we derive from the electric field boundary conditions, and the equation on the right is what we derive from the magnetic field boundary conditions. Let's go ahead and manipulate these two equations. The first thing, we have an expression for the amplitude of the transmitted electric field. So we can replace this term with E naught I plus E naught R. That's our first step. Then we can expand this right-hand side of the equation, write this as the sum of two ratios. And so we're here, that's all we've done. Now what we want to do is we want to move both terms containing the amplitude of the reflected wave over to the left, and then both terms containing the amplitude of the incident wave over to the right. And we end up here. The next thing we'll do is we'll multiply both sides of this equation by eta 1 times eta 2. When we do that, those impedance expressions inside the parentheses simplify down a bit. Now we're in a position to solve this last equation for the amplitude of the reflected wave divided by the amplitude of the incident wave. We'll take this term, bring it over underneath the amplitude of the reflected wave. We'll take this expression and bring it down to a denominator underneath this. And that is our very definition of the reflection coefficient. And we see it's this very simple equation. So one thing we can conclude right away, fundamentally it's a change in impedance that causes a wave to reflect from an interface. We also see that there's a negative sign here. That means we can get a reflection coefficient that is negative. Now that's not really a magical thing, that just means the reflected wave has a 180-degree phase shift relative to the applied wave. Now we'd like to derive an expression for the transmission coefficient. So we start with the equation we derived on the previous slide and we solve that for the amplitude of the reflected wave. Then we'll go back and we'll start again with this equation that we derived from the electric field boundary conditions. Notice there's this amplitude of the reflected wave here. Well, we now have an expression for that. So we can take this term and plug it in here to eliminate the amplitude of the reflected wave. When we do that, we end up here. Now both of these terms contain the amplitude of the incident wave, so we can factor that out and we're left with this expression inside of parentheses. At this point, we can take the amplitude of the incident wave, bring it over to the left side of the equation, so we have an ET divided by EI. That is our very definition of the transmission coefficient, amplitude of the transmitted wave divided by the amplitude of the incident wave. So this is the expression we got from the top. We can do a little bit of math, and we can say that 1 equals eta 2 plus eta 1 divided by eta 2 plus eta 1. We now have a common denominator, and then we can combine these terms, and we derive our final expression for the transmission coefficient. Again, defined as the amplitude of the transmitted wave relative to the amplitude of the incident wave. And it is just 2 eta 2 over the sum of the impedances. Now we would like to derive a relationship between the two. So we start off again with our expression that we got from the boundary conditions of the electric fields. And we divide everything by the amplitude of the incident wave. Once we do that, we notice that this term is 1. This term becomes our definition of the reflection coefficient, and this term becomes our definition of the transmission coefficient. So we can replace all three, and we just have 1 plus R equals T. And so that's a very simple equation relating R and T. So if we calculate one of those, this is probably the easier equation to use to calculate the other one. Now later, when we start getting to power, these terms do not relate power. They're talking about amplitudes of waves. But later on, we talk about power, we're going to have an equation that says if you add up the fraction of power that gets reflected with the fraction of power that gets transmitted, those have to equal 1. And so we have an R plus T equals 1. But that's not what's happening here. It looks similar and often confused with the conservation of power equation, but little r and little t are not power quantities. When we do talk about power, reflectance and transmittance, when we get to that, we'll use capital R and capital T. So don't make that mistake. Little r, little t are talking about amplitudes, and they don't obey a conservation of power. Let's end with some final notes about scattering of waves at normal incidence. First, in many texts, instead of seeing lowercase r for reflection coefficient, you'll see this symbol gamma. And that's fine, it means the same thing. I like to reserve gamma for when we're talking about signals on a transmission line. And in fact, it means the same thing. We will still use it to relate reflection of signal amplitudes. I'll just use that when we talk about transmission lines to help us remember that we're talking about something that's physically different than a wave hitting an interface. We'll be talking about signals on transmission lines. We saw that in our equation for the reflection coefficient, there was a difference. And that means if the impedance in medium 1 is greater than the impedance in medium 2, our reflected wave will get a 180-degree phase shift relative to the applied wave. We had this little rule that relates our value of R and T, 1 plus R equals T, and remember R and T relate field amplitude, so that is not a conservation of power. And that confusion won't even rise now. That confusion will arise once we talk about reflectance and transmittance, and then we have this equation R plus T equals 1 that looks similar to that, but it's capital R plus capital T equals 1. So when that time comes, don't get confused. We need to remember that the reflection and transmission coefficients are unitless, right? Because the reflection coefficient is the amplitude of the reflected wave divided by the amplitude of the incident wave, so the units cancel. And last, if we look at the magnitude of R and T, they are bound to be between 0 and 1. That is assuming that we don't have any gain in any of the materials, in which case it probably could be greater than 1. So they're bound between 0 and 1. This is a great check when we do calculations. If we get 2.3 for our reflection coefficient, we can be sure that something's wrong.